Alright, I got a fun one for us today. We're going to go back to hardware and computer design, and we'll talk about some more pieces that make up a CPU and how to build them. Alright, so yeah, this is fun, and this is honestly one of my favorite lectures from this class, because if I think back to when I took my own version of this class at Fresno State, this is like when I really started to feel like I understand how computers work, like how all these logic gates work together and actually give me something that I can program. So it's really, really cool. It felt magical when I first learned it, and I will do my best to pass the magic on to you, my students. So let's get started and talk about a circuit that adds numbers, because that's something that a computer, you'd like it to do, right? We want to make a computer that can do math. That's why we invented these guys, right? So let's first talk about how to go from truth tables to a formula in logic using some combination of and, or, and not, usually. Okay, so here's a very easy process that you could go through, and it will always give you a formula. And so the idea is we have like we have a question mark or something. Pretend this is a question mark. This is the truth table that I would like to generate. I'd like, when A is true and B is false, I want a 1 here. When A is false and B is true, I want a 0 here. And for all of these, I want it for these exact combinations of input A and B values. This is the output. Like this is the this is like the equality on the two. Okay, so like we want to figure out what is this logical formula that does this exact thing. Okay, I know that if you stare at this long enough, you'll be like, oh yeah, this is just A exclusive or B, and then you negate it. But I want to teach you, even if there aren't any tricks, or this is something very long, there's always a way to get it. Okay, so let me show you that. Here is the secret. What you do is you look at the rows where the output is a 1. You only care. We're going to only care about where there's a 1. We're going to forget about where there's zeros, because those are not going to end up mattering. So we're going to look at these 2 rows. Those are the 2 rows that I must produce a 1 in for my final formula. Okay? And so the secret is to always produce, maybe not a simplified answer, but an answer that will get you this. Here's the trick. You're going to AND together all of the inputs, and you will negate any of the inputs that were 0, so that the expression always evaluates to 1 when, because that's what we're trying to get at, a 1, when those inputs were set to those exact values. All right, so when A is false and B is false, so I'm going to AND together a combination of A and B. If there are any zeros, I'm going to negate them. So I want not A to be true, right? I want not B to be true. I'm going to AND together those. So this is the symbol for logical AND. These are the symbols for negation, all right? So that's what I'll do. So I have that one, okay? And do you see how when A is 0, A is false, and B is false, that will produce true, right? This will generate true, this formula. And so that kind of gives you that chunk. And we're trying to find this chunk next, okay? So we'll do this one, all right? How do we find the formula for this one? We have an A and a B involved, and I'm going to AND them together if they're true, and I will negate any of the ones that are false. None of them are false. So it's just A and with B. Do you see how if A is true and B is true, A AND with B will give you a 1? That's what I want. And then you're pretty much home free, because then what you do is you OR together all of those expressions that gave you a 1 on those rows that themselves had 1s. So we take this guy and we take this guy and we OR them together, and if you use this to generate a truth table, it will give you exactly this. All right? I hope that makes sense, and I hope you see it. If you don't, try it. Try and generate the truth table for this exact formula. It's going to give you that. Isn't that cool? Because now you can make a circuit for it. And so you know how to build a circuit out of transistors and or logic gates now, and so you can do whatever you want. Whatever computation you want done on some inputs, you can produce now, and that is key. All right. So here's my question for you. You try it. So here are some inputs. A and B are inputs, and then here are some things I'd like to do on single bits A and B. This is every combination of what A and B could be, 1s or 0s. And here are some outputs that I really would care about. I'd like to be able to add together A and B as a single bit. And this is the sum of them, right? Because they're like 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1, 0, because we got to carry a 1, right? So it's 0 in the output for that particular row, though. in the output. So there's that one, and then there's also, here's another separate output, a carry out. Like when I'm adding 2 zeros or a 1 and a 0, there's no carry, right? But if you're adding a 1 and a 1, the sum in that digit place is a 0, but you are carrying that 1. All right, so this is kind of what we're representing. So the sum of these guys, let me go back to blue. The sum of these guys, like 1 plus 0, the answer is 1, and you don't carry anything out, okay? Or, though, if it's like 1 plus 1, the answer is 0 here, but you do carry out a 1 because the answer is 1, 0, yeah? It's really supposed to be 1, 0 at least. So your job is to create logical formulas for sum based on A and B, and then also carry out based on A and B. All right, that's your goal right now. So give that a try. Let me go to the other side quickly so you can see the setup. This is the process, and now you give that a try. All right, so I'd like to be able to do like I want a formula using A and B for sum, for the sum of those bits. Okay. So okay, what is sum? It's going to be, all right, where is it a 1? That's what we look at, right? It's a 1 when A is false and B is true. A is false and B is true, or when A is true and B is false, or A is true and B is false. See how I'm reading it off? So that's one thing. And you know that this is exclusive OR. Okay, so apparently summing bits, single bits, is the same as exclusive OR. That's pretty cool. All right, so even if you don't know that it's exclusive OR, you can still build it out of and or not. Okay, because that is functionally complete. And then what about carry out? Well, we only have a 1 in one spot, and that's when A is true and B is true. So our carry out formula, how do we know when to carry out? That's when A is true and B is true. There's only one option there. All right, I hope you got that. Hope that makes some sense. But like, we know how to add bits now. That's pretty cool. Let's start building circuits that add these bits together, because then we can like chain them and add multiple bits, and then we're suddenly adding registers. Cool, huh? So yeah, some can be an OR gate. That's fine. Or sorry, an exclusive OR gate. So here's the sum, exclusive OR gate, and then the carry out is an AND, right? You AND those two guys together, and then we have 1-bit addition. That's our adder circuit. We can make this a blue box and make it opaque because we know how to build it now, and we can start chaining these guys together for abstraction purposes. All right, and we like to simplify carry out. We call that like C subscript out a lot. You'll see that. So yeah, this is our final circuit, and it adds 2 tiny numbers, 2 bits, 2 individual bits, perfectly right. Okay, so the reason we want to zoom out is so that we can build a 32-bit adder circuit. All right, so how do we build a multi-bit adder? So we're actually going to need, in addition to carry out and the inputs, we're going to need we're going to need a carry in. That's a third input. We're going to need a third input because sometimes you need to carry in, and that's part of the things you're adding into your output sum and your carry out. Okay, let me prove that to you. For the first bit in your addition, you never need a carry in. So like if let's pretend we're adding 4-bit numbers, 0, 1, 1, 1. For the first 2 bits, you don't need a carry in. It's always, there's nothing there. It's okay, 1 plus 1 is 1, 0. And now you suddenly have 3 digits, right? You suddenly have 3 bits to add because potentially from your previous bit now you have something new, something that we carried over. So that you need a third input. In addition to the bits that you're already adding, you need this carry in bit here, okay? And so we need to make a fancier adder circuit. We need a carry in kind of thing that works kind of like this. So third input, like a carry in addition to A and B, and we got to build the truth table. We need a new formula for sum, all right? So if you think about it long enough, it's just you tack on another exclusive OR, honestly. So we need another way to compute sum and carry out with these things, like 1 plus 1 plus 1 is a 1 in this position, then you also carry out, right? Then you also carry out another 1 to over there. So sum is 1, carry out is 1, or if the carry in now, it's like carry in is 1, you're adding bit 0 to bit 1. What's the sum here? It's going to be 1, 0, right? So you carry out a 1. Well, you carry a 1, and then the sum is 0. So sum is 0, carry out a 1. So we have to like formulate these new formulas for this fancier thing that has a third input. I believe that you could do it. Try it. exclusive OR will give you the answer for sum. Just keep using it. That's my hint. But yeah, let's change our design to have a carry in always, because you can just set it to 0 for the first one. That's fine. Okay. So let's take advantage of that. Let me finish this addition. It's 1 0, right? 1 0. And we carry that one more time, and that's our final answer. Yeah. So that is our full adder circuit. Okay. Some people call this a half adder because it's not it doesn't take a carry in. This is called a full adder now. Okay. So let's take these guys that have carry-ins as well as the bits and a sum and a carry-out, and let's chain them together, because like that's all we need, right? If we just started chaining together the carry in, the carry out of the previous one, this is the carry out of the previous one, into the carry in of the next one, do you see how that'll give us what we want here? So here's my 4-bit adder. All right, let's add 4-bit numbers together. So here are my two numbers that I want to add, each of their bits. Let's hook into each of those, like we have a 4-bit register. And then our initial carry-in to the first adder is 0, right? Because there's no carry-in to the first thing. Now it's 1 plus 0 plus 0. And then you have a sum bit, goes here, right? And then your carry-out becomes the carry-in to the next adder. Do you see that? That's the goal. That's how this works. So yeah, as long as you just keep chaining things, and suddenly you have a 4-bit adder or a 64-bit adder for our purposes. It's like you got 1 plus 0, like the sum is 1, and you're carrying out 0, and that becomes the carry into the next one. Now it's 1 plus 1 plus 0, right? And then you're going to carry out a 1, but the sum is 0. Is that, you kind of see how that's going to work? And now it's going to be 0 plus 1 plus 1. Again, it's 1 carried out, and the sum is 0. And now, again, 1 plus 0 plus 1, sum is 0, and you carry out a final thing, a 1, so it kind of overflowed, potentially. Okay? So that's beautiful. And now we have 4-bit adders, or 32-bit adders, or 64-bit adders, and we can just we can make a big box for one of those. And so the initial carry in, you just set it to 0, and you're off to the races. And this is a simplified drawing, or this is kind of how it works from now on. If you have very wide wires, you're going to do a little slash here, and you're going to say how many bits are really there. So it's really, this is 4 tiny wires, right? A is 4 bits. That's what it's saying. B is 4 bits. Carry in is just a single bit. Carry out to the last bit, after the last bit, is a single bit, but the sum is a 4-bit answer, 4-bit output. Okay, that's how you read that. So yeah, yay for abstraction. Well, now you can like chain together a bunch of 4-bit adders to make a 32-bit adder, make your day easier. Isn't that cool? All right. So now we can add numbers. We can do addition in a CPU. We can build this. We can build this circuit with ands, ors, and nots. All right. We know how now. Isn't that magical? That's something that computers can do. Like, we just build a part of a computer. All right. Next, we need to talk about something called multiplexers. So a multiplexer is a way to pick out from a bunch of different potential inputs, like one that you really care about. And so, for example, when you do like a move instruction, move from like x6 into x7, you need to, like the CPU as it's executing this, it's like, all right, I need to go into the register, all of my registers, and I need to pick out just the x6 value, please. So we call it multiplexes over all the registers, and it picks out the register it really cares about. All right, so that's what's going to happen. And yeah, let's talk about multiplexers. They're used a lot in the control circuitry for our CPU, and that's the piece that's like the conductor of the symphony. It's telling everybody what to do. It's like, memory, give me this. Okay, we're going to do an add instruction. Let me get the registers and get those in the right place. So the control circuit is like the conductor of this symphony that is your program, and it talks to all the different pieces of the CPU to execute instructions like it. It's where all the wires meet, right? You got all your registers and the CPU and stuff. The control circuitry is saying like, all right, you want to load and store a value? Here, I'm going to send to memory, hey, give me this address. And then the memory is going to send back along the bus. It's other data bus, right? Control bus, data bus. Give me this. All right, you wanted this? Here it is. And it sends it back, all right, on the other lane of the highway. And then sometimes, like the control circuitry even says it talks to devices, like maybe a hard drive or something. Like, okay, this thing isn't in memory yet. Let's get it there. Okay, That's kind of what the control circuits do. They're talking to everybody. They're hooked into everybody. And a multiplexer is a type of control circuit that selects or chooses or multiplexes one of a bunch of values. It lets you pick out something. All right. We say mux for short. All right, for multiplexer. And so, like for example, a multiplexer can choose X4 to read out of all the potential registers in your CPU when you like execute this one, because it's got to go into X4 and shove it into X0, right? So kind of here's what's going on. You got your control circuitry. The control circuitry of the CPU. Part of that is a multiplexer, which we'll call MUX for short. And you have to say, all right, I would like multiplexer. I would like a specific kind of register. I would like register X4, please. All right. And so the multiplexer is hooked into every single register. It's like hooked into X0, has a wire going out and in to X1, X2, ... all of them, fans out forever, including X4. And then it also, the control circuitry has to tell the multiplexer, like, this is the one that I want. There's a selector bit, or set of bits, that also feeds into the multiplexer. There's two inputs. It's like, right, this is the input and like this is the output. I would like you to select for me, please, X4. So it like encodes X4 into that, and then it pulls that. The multiplexer knows to pull into X4 and like output it along this wire. Okay, that's pretty vague right now, but we'll get there. Okay, so a multiplexer just chooses one of several values, and here's kind of how you draw it. All right, here's how you really draw a multiplexer. It looks like a little trapezoid, and it takes a couple inputs. It takes all the things that you want to multiplex over. These are your options, right? And then it takes a selector, which may be a fat wire, because you might have to select over multiple things. For this particular one, this is secretly 2 wires. This part is secretly 2 wires, because you're selecting over 3 things for this example. And then you have one output. This is the thing that you're trying to, like, you're trying to hook into one of these. Like, I want C, or I would like A, please now, or I would like B, please now. So you tell the selector which one you want, like you encode C, and then the multiplexer knows to send C to the output rather than the other two. That's the goal of a multiplexer, right? So an n-way multiplexer in general has a bunch of n input values and a single output value, and we select from the inputs to produce our output, okay? And so now the question is, how do we choose which input to select? You have to give us another input along a wire or a set of wires to choose what you need. Okay, so there's an additional input value, select, called S, which encodes in a certain way which of those n inputs you want to shove into the output. All right, so for example, if you want to choose one of 3 things, you have to encode this into binary. So you can be like, all right, 0 can be A, and then 1 can be B, and then you notice you have no room for C, so you have to add a new bit. So let's say 0, 0 now means A, 0, 1 means B, and like 1, 0 means C. And then 1, 1, like that's still there, that's a possibility, we're just not going to care about that one. All right. So you need 2 wires, 2 bits coming in, that is your selector, 2 bits to select, like, was it 0, 0, 0, 1, or 1, 0? And then you send that in as input. Like let's say we want to select C, so we'll send 1, 0 in along our selector, and that will cause the multiplexer to take the C and send that into the output and like cut off these guys. All right, that's the goal. So yeah, every multiplexer is drawn using an isosceles trapezoid, apparently. That's how we like to do it. And it's like, kind of makes sense the way it's working, because it's like, this is the wider part. It's all these things are being funneled, right? You're getting one thing out. They're being strained or something. Okay, so that's a 3-way multiplexer. And now the goal is, all right, how do I use logic gates to build this? Because this is useful. This is used in registers, for example, and as we're executing the move instruction over multiple registers, we've got to pick one out. Okay, so here is a question for you. Let's try and think about it. So let's pretend we have 42 different values along a single multiplexer. It's a 42-way multiplexer, and we have to give in some selectors, right? Some encoding, and like to say I want input 42, that's my output right now, or I want input 2, that's my output right now. So we have to encode each of these in some way. So my question to you is, how many different wires must S have at a minimum? Is it really fat or is it really skinny? Who knows? Figure it out. Okay, How many wires do we need at a minimum to be able to choose one of 42 different values? And there's a hint with this picture. It's if you've watched Twin Peaks, this character has a special name, and the answer is in her name, or a way to find the answer at least. Okay, so did you get it? Let's think about this together. So, well, if you use just one bit, you have just 0 or 1 to work with, you can only talk about or ask for one of 2 different things. We have 42. That's not enough, all right? If you use 2 bits, how many options can you choose from? 0, 0, 0, 1, 1, 0, 1, 1. That's not too bad, right? So there is a pattern going on. If you use 1 bit, you get 2 of the 1 options. If you use 2 bits, you get 2 of the 2 options. If you use 3 bits, you get 2 of the 3 options. That's 8. Still not enough. 2 of the 4 bits, you get that many, 16 options. Still not enough for us. 2 of the 5, still not enough for us. That's only 32. 2 to the 6, though, that's the sweet spot. That gives you 64 things to choose from, and that's enough to cover 42. You can just, there will be some left over, but like you can't go any less than that. Do you see that? So the answer must be 6. Okay, so there must be, this is a chunky wire with 6 inputs. All right, so your inputs get to range from 0, 0, 0, 0, 0, 0, all the way to 6 ones. And some of them you won't use because you only need to encode 42 different things. Some of them won't matter, but you need at least 6 bits, all right? No less than that. At a minimum, the reason I asked at a minimum is because, like, technically, yes, you could use 42 wires, but that's overkill. Then you'd be able to choose among 42 different, 2 to the 42 different things. How many is that? That's way too many, right? Python 3, 2 to the 42. That's a disgusting amount of things. That's overkill, okay? That's extra wire, and like copper is expensive these days, so we don't like that. So at a minimum, C is the answer, and the trick is you can use the log base 2 to figure this out. So import math.log, is it underscore log 2 of 42, and you got to round up. So it's 5 point something, so you need 5 and fractional bits to encode 42 different things. So we can only have a whole number of bits in a circuit, so we have to round up to 6. Okay, that's how that works. So I hope that makes sense. And so that's we're going along our way now. We can kind of think about encodings. And so let's try and make a selector circuit. All right, let's try and build out this multiplexer. Let's say we have not 42, not 3. Let's say we have let's see. How do I want to do this? Let me Yeah, let's get at this almost. We don't have a multiplexer yet. I think that's what I want to say. Let's try and understand encoding and picking out, like, okay, when it's exactly 1, 0, I want C. All right, how do we do that? How do we take C's value only? So this is going to help us, right? I would like you, I'll give you a lot of hints right now, to write a logical formula to output the value of the variable Z. Let's pretend we have 4 variables, all right? A, B, C, D, and Z. We have 4 variables, and we care about Z's value as outputting it, all right? I'd like to output the value of the variable Z only when A is false, B is true, C is false, and D is true. I would like to output the value of Z only in this case, all right? I would otherwise, if these values are not like they are, if A and B and C and D are something else, some other combination of trues and falses, I would like you to output false always. So who cares what Z is in that case? If these don't align, output 0 always, all right? Whenever A, B, C, and D have some other kind of value, okay? So, for example, if A is false, B is true, C is false, and D is true, then we output whatever Z is. So Z is a 1, we put a 1 here, all right? If, again, they align and Z is a 0, we output a 0, because that's whatever Z was. We preserve Z in that case for these inputs, all right? Preserve Z. If it was a 1, output a 1. If it was a 0, output a 0. In any other case, like if A was not false, but everything else was right, doesn't matter. Whatever Z is, we don't care anymore. Output a 0 always, all right? That's what we want here, all right? So essentially what we're making right now, what I'm trying to have you make, is a 4-bit selector circuit. So you're looking at 4 bits and you're trying to select a value of 1 bit out, okay? So can you figure out, take a second to see if you can do it, like, can you encode this idea and taking z and making it the output whenever this the clouds part and everything aligns. Can you figure it out? If you need a hint, let's encode this idea. Whenever A is false, this is true, right? A is false and B is true. This is what I want. And C is false and D is true. This is going to be part of our output here. Okay, it's going to be very important. That's my hint to you. So can you use this and maybe use some other formulas? Add on some more logic gates. You're going to need to use Z, of course, to produce a 1 or a 0, or a 0 if any of those don't match. All right, so let me give the full answer away now. Do you see that this right here, this bit, this is going to always, it's going to be a 1 whenever we care about outputting Z, right? Whenever A is false and B is true and C is true, C is false. Oh, I forgot it. Excuse me. I forgot one of these. C is false and D is true. See? That's what I want. Do you see how that's always going to be a 1 only in the cases that I care about outputting Z? Always going to be 1 in the cases that I care about outputting Z. It'll be a 0 in any other case. Like when A is false, that makes this whole, or sorry, when A is true, this makes this whole thing false. See that? So only in the case that I care about it does this become a 1. So this is my encoding that selects Z. Encoding that selects Z, because do you see that? All right, now if it's a 1, if it's guaranteed to be a 1 when I care about outputting Z, if I just ANDed this with whatever Z was, then I would get my answer. Because if this aligns and I am supposed to output Z right now, do you see how it will? If this happens, then I do have a 1 here. And then whatever Z is, if it's a 1, 1 ANDed with 1 is 1. If it's a 0, this is going to be a 1, right? And I'll still AND it with Z, and Z happens to be 0. So I do get 0 out still. I'm still getting Z's answer. But if any of these don't align, it doesn't matter what Z is, because this is going to be false, right? And false is going to force, right, when you AND it with anything. It'll force a 0 in the output. So do you see how this magical formula, based on my particular encoding of A, B's, and C's and D's, that gave me Z's value if I just ANDed it? So this is a magical formula. This is a way to select things based on an encoding, okay? This idea, I hope you see it. That's something you have to remember, okay? That's the secret. This was my encoding. Just AND it with whatever I want to preserve whenever that is true about that. Like I have these particular values for my inputs. Then I want to pass along Z only, okay? And this will finally let us build a multiplexer. All right, let's pretend we want to build a 2-way multiplexer, 1-bit 2-way multiplexer. So you got one, you only need one selector, right? Bit 0 means A or something. Bit 1 means I want B, let's say. Or maybe it's the opposite. Let's see what we're trying to do here. Let's say that when the selector is 0, I want B's value, whatever it was. So like here it was, I want to preserve this guy. When the selector is 0, it's B's value apparently. All right, that's what I like. That's what I want. And then when the selector is a 1, I want to preserve A's value. That's what I want to pass along. That's what I want to multiplex over. All right, so when S is a 0, I want to take B and make that the output. When S is a 1, I want to take A and make that the output. All right, so let's try and build this idea. All right, so technically this is just a truth table, so you could figure it out, but this generalizes better this idea that we're talking about here. Okay, so okay, when S is false, I want B's value. All right, using this idea, how do we encode this? So when S is false, so when not S is true, I want to preserve B's value. Take the 1 if it's a 1, take a 0 if it's a 0. I AND it with whatever I want to preserve, okay? So this little sub-formula, it takes B's value and outputs it. Takes B's value when S is equal to 0, when S is false. Do you see that? When S is false, this is a 1, and then it preserves B, whatever it was. All right? Convince yourself that that's true. And then the same thing for A. So when S is a 1, so when S is true, and I want to preserve A's value. So AND it with A. Do you see how this will take A's value whenever S is true? Because this will be a 1. Then we're ANDing with whatever A was to preserve it. This takes and preserves A's value when S is 1. And these are two mutually exclusive cases. It'll be false, right? When S is when S is like a 1, it wasn't false. This part will be 0, and then also if S is false, this part is also going to produce a 0. So they're not going to cancel each other out. They're doing two separate things, right? They're only going to be true in separate cases. So my final output that encodes how this multiplexer should work, what is my output formula? It's these guys ORed together, all right? So when S is false, I want to preserve B in that case, or when S is true, I want to preserve A. Convince yourself, right? This is my formula. Go check that it works. See if you can understand it. All right? It's just a truth table all over again, honestly. We're just trying to figure out the truth table, but this can now generalize to make like multi-bit, multi-way multiplexers. I said the word multi a lot in that sentence, but that's the secret. All right? This picks out B when S is false. This picks out A when S is true. They are mutually exclusive, so you can OR them together and not worry. Okay? And that will produce this output row. So see if you can check yourself, check that this works, and that you understand it. And now we can do whatever we want now. Okay, so this is beautiful. So let's see. Dun, dun, dun. I think first of all, this is we'd like to build now a 4-bit two-way multiplexer. So we have 4-bit values. We can chain what we just did, essentially. We can chain them. Sorry, I should tell you that here's the circuit. Here's the actual circuit. Here's the output. We figured it out. Selector value. It's all working out, and then we can zoom out and make many of these. Okay. So for example, if you wanted a two-way multiplexer over two 4-bit values, that's what the slash means again. This is what I'd like to build right now. Two 4-bit inputs, right? And I still need just 1 bit for a selector. It's I would like to output just A or just B, but now it's 4-bit thing, so it's a 4-bit output. That's what the slash means again. Boop. You can chain together these smaller ones to talk about the bigger ones, because this selector, you just feed it in each time, right? Just take A's thing or take B's thing, hook into the same selector value, and then if it was a 1, we're taking the A thing, right? So that's the idea. If 1 is sent in here, it's always going to take A. It's going to prefer A's stuff because that's what the selector wants. And then now you're outputting a 4-bit thing. I hope that makes sense. Okay, that's the secret. So that's how you can build up bigger multiplexers. And I encourage you to think of how would you build this 3-way multiplexer now with 2 input S wires, like S1 and S2. See if you could encode it. I think you could. So yeah, we can start zooming out again, and now just the magic of abstraction takes over. It's really, really cool. That's how it works. So yeah, let me try now to build for you a 4-way multiplexer. All right, the 1-bit 4-way multiplexer. So we got individual bits, A, B, C, D are their single bits, and we have a selector which needs to be 2 bits. Right, the selector must be 2 bits now because that's the only way that you can select over 4 things. It's the minimum amount. So let's have this be our encoding. When the selector bits are 0 and 0, we output A's value. Selector bits are 0 and 1, B's value, 1 and 0, C's value, 1 and 1, D's value. Okay? So again, it's the same pattern. Same exact pattern. And this is like S1 and S0, let's say. So when S1, S0 look like this. When they're 0, 0, I want A's value, 0, 1, B's value, 1, 0, C, 1, 1, D. Okay? And so this is really, I should put a /2 here, shouldn't I? And if you think about this long enough, this all makes sense, right? What's the formula for if I want just A? I want to preserve A. That means I got 0. S0 was false, and S1 was false. S1 was false, S0 was false. If so, I want to preserve A's value. I want to select out that one. And I just keep on ORing with every other option, right? If S1 is false and S0 is true, that's our 0, 1. Then I want to preserve B's value. Yeah, make it a 1 when it needs to be. And same for C, that's true, false for S1 and S0. And then finally, true, true, preserve D's value, whatever it was. And so you can see how that's working out. We're negating some things. This is an AND gate that takes 3 things and ANDs them all together in some order. You can imagine that this is built of 2 smaller normal AND gates, right? You gotta like AND these together first maybe, and then take this one, AND it with the result. That's kind of how that might work. And same for this like 4-bit OR gate. It's like ORing together these 2 things maybe, and then ORing together these 2 things. Sorry, I need more ORs, don't I? So first we have to OR these guys, then these guys, and then one last one, don't we? Boop. So that's kind of how it works. It's just ORing a bunch of things together, just like this was ANDing a bunch of things together. Okay. But yeah, the circuit is as you would expect now that you know how to encode things. And this, slowly but surely, you can build this up to be like a, what do we need for our registers in ARM 64-bit land? We need a 64-bit 32-way mux, right? Because we got like 32 registers, something like that. So that's what we need in our CPU somewhere. There is secretly one of those. All right. But I hope you can kind of understand how to build them all now. How these multiplexers can select out what we like. All right, and you can make these fatter, like you can have more options, and then also wider in the other axis, where you can like take and chain a bunch of these smaller ones to like take a bunch of bits at once. Okay, so yeah, I think that's what I wanted to tell you. And now we're ready to talk about a big piece of circuitry that uses adders, like we learned, and multiplexers, like we learned, to do just random arithmetic stuff. So let's talk about a magical thing called an ALU first. So an ALU is a place inside of your CPU that does arithmetic and logic. So we call it the arithmetic logic unit. All right, ALU for short. What it does is it performs arithmetic and logical operations. That's just a place in the CPU where that happens. All right, it just does a lot of those things. It's just like it's a one-stop shop for a lot of cool stuff. So, for example, let's say that we have a simplified CPU that can only do bitwise or bitwise and addition and checking for equality. Let's say that's the only thing that our CPU can do, so that's the only stuff that's going in the ALU. Our ALU for 64-bit ARM stuff can do plenty more. But this is a good start, okay? So if you think about it, this is kind of what we're building. I want to shove in like 2 register values, like 64 bits here, 64 bits here, in the worst case. And then I want to be able to do either or addition and or equality checks on those 2 inputs. And so essentially the magic of a CPU is you can just do them all in parallel. Like this is just electricity flowing. You can do them all at once and just take the answer that you really wanted by multiplexing. Okay, that's pretty fun. So this is, if you have 4 things, you need a 2-bit opcode. All right, this is your selector. Right? You need a 2-bit selector, which we call an opcode in this case, because it's short for operation code. Which operation do we want to do? That's the selector that we fit in. Did we want to do OR? If so, give the encoding for OR. That's the operation that I am encoding. Okay, I hope that makes sense. So yeah, 3 inputs total that could be wide and have a lot of wires along with them, because they might be multi-bits, multiple bit things. So yeah, 2 64-bit values. Just do all these operations at once, and then multiplex out the one you wanted as your result. And we call the selector, in this case for the ALU, the opcode. All right, operation code. And then the outputs are like the result, if you wanted that. Like, was the answer true or false? What was the bitwise addition thing? So this is another 64-bit output, because you need that. And then, so you have that. You always need a result, because that needs to be shoved into a register usually, like in an addition instruction. Yeah, so opcode is operation code. Might as well write that down. Operation code. And then you also have condition codes that get set, potentially. So like, you can have a circuit that checks for was the answer 0, and if so, like that'll go in and it will set like the Z flag, right, inside of one of your condition registers, NZCV. So this is based on the result. Based on the result. It'll like go and set a condition, because you can check that and like have it go feed into that. That's pretty cool, right? So yeah, those are the outputs, and yeah, once you know how to build it, you just like hook in all the different things that you want, feed them into a multiplexer, select over what you'd like as your output, and maybe also feed into the output to go to your flag registers. Okay, that's what you do, and then you can zoom out, call this a box, call it an ALU, and it looks like a pair of pants. Okay, so that's the secret. That's what the ALU is when you zoom out on it, at least. So you got your opcode, inputs, result, and output condition codes as well. So that's it. This is like a very key piece of a CPU that you now know how to build. Isn't that fun? So yeah, let's keep on trucking, because there's more that you can do, right? And instead of addition, you might want to do subtraction because you have a sub instruction. All you need to do a sub instruction in assembly, to do this, just like all we need to do is feed it into an addition circuit after we negate the second thing. So we just need to learn how to negate something, right? So to negate a number, what do? How do we encode it, right? You got to flip all the bits, and then you add 1, okay? That's how you do it. We've learned this. So how do we build a negation circuit? Or how do we build a subtraction circuit? Well, you've got A, your input A, you got your input B, 64-bit values for 64-bit ARM stuff. And then, all right, you need to eventually add things, but first we need to negate B by, I don't know, flipping all its bits. And then we need like an add 1 circuit, add 1, and we add that with A, and that's somehow, now we've subtracted these things, all right? And then the output, the output can come down here or something. This is our subtraction circuit, right? You can build it from the other things. I think you know how to build an adder. You know how to build a flip all the bits gate circuit. I believe that you could. A bunch of knots everywhere, right? And then you could just have a add 1 circuit very easily by always hooking in, like make an adder again and just hook in the input to be a 1 in the lowest bit and a 0 everywhere else. That's how you encode 1, right? There's your +1 circuit. That's the number 1, at least it's supposed to be. Like this is your output. You feed that in. Feed that to wherever it needed to go. Like we're shoving it into a register. Out. That will hold A minus B, won't it? So you can build that circuit, can't you? Just you know the constituent pieces now. You could build each piece, and now you suddenly have a subtraction circuit too. Okay. Multiplication, that's also not too bad. Let me show you how to multiply in binary. It's this guy. Honestly, it's simple to multiply 2 binary values together, because it's never have to like memorize times tables. It's always just a bunch of shifting and adding. Watch. So 1011 times 1110, let's say. Well, it's like, all right, it's all this times a 0, and the 0 just like makes nothing, right? So it's just a bunch of zeros. You see that? So if it's all a bunch of zeros, you take nothing. It's all zeros. And then you shift over, and now you're ready for the next place, right? Now you're ready to put stuff over here. And if it's a 1, right, you just take the thing. Because 1 times all this is that thing. So 1, 0, 1, 1. You just take the thing again. So it's really, you're just shifting based on the second thing. You're just taking this number and either adding it or not adding it. You're not adding it. If it's a 0, you shift it over. And if there's a 1, you add it. Shift it over, there's a 1, you add it. Shift it over, there's a 1, you add it. And so your final output looks like this. Does that make sense? That's the secret. That's how that works. So it's just like, all right, if there is a 1, just like it feeds into all of these, and you just take the whole thing and you place it there where it needed to go. So the way to build a multiplication circuit, I'm not going to tell you how. It's a little complicated, but I think you can imagine it slightly at least. You're going to need an adder. You need to add into like a final output place. You're going to need to be able to shift. You need a register that shifts by a certain amount. Because like, all right, when you're working on this place, you need to shift this over by 1. When you're working on this place, you need to shift it over by 2. And then finally, an accumulator. Okay, an accumulator is a piece of memory that you can use your adder to keep adding into. So like you're accumulating into this final answer down here. Okay, so like make that a register. So yeah, it's got to be a piece of memory that you can keep on adding into, setting and resetting. I think you get the idea. Okay, so that's multiplication. I believe that if you squinted hard enough, like you could, and you tried for a while, you could make one of these. It's not that bad. So I'm not going to show you though, because it is pretty complicated. So, but you could make it. You know all these pieces. I believe that you could build it up. I've told you how to build up all the pieces, more or less. So yeah, we can more or less make some key pieces of a CPU right now, and that should make you feel good about yourself. All right. Last thing I want to talk about is a FPU. That's short for floating point unit, because everything that I've been talking about right now is whole number stuff, integer arithmetic. I told you how to build integer adders, right? I haven't told you how to do like double computations, float computations. The CPU is where all of the whole number stuff happens. There's a separate place on the same chip, though, called the FPU that has floating point operation abilities. All right. So this place, FPU, lives on our chip. Here's an example: potential ARM chip that has an FPU in it, among other things. It's the other place in the processor that has floating point capabilities. Right? It has its own registers actually, and we'll learn their names later. It has its own little registers that can hold doubles and things, and it knows how to add together floating point numbers and stuff like that. So you kind of like the CPU is saying, hey, FPU, take care of this, because you're working with doubles right now. And then like it'll give you the answer back when you're ready to like print it or something. So yeah, we'll have a whole lecture dedicated to floating point numbers, but not yet. Okay, so I think my answer, or what I want to say, is just hold on, just wait, and we'll talk about that too. But it's a separate place, all right? It's a separate place. It's not part of the pants that make up the ALU. Okay, so yeah, I think that's all that I wanted to say about how to build some more pieces of a CPU. Hopefully, it seems kind of magical, but also not too magical because we know how to build them all now. All right, so yeah, I think that's what I wanted to say, and I will see you in the next lecture.